Welcome back to the Deep Dive. This is where we try to boil down some pretty complex technical research. Make it easier to grasp, give you that shortcut.
Yeah, exactly. And today we're getting into something pretty fundamental in engineering materials.
Specifically, we're looking at how to make certain structures tougher, especially when they're under a lot of stress.
That's right. We're talking about fiber reinforced polymer composites, FRPs. You find these everywhere now. Think huge wind turbine blades, parts of aircraft wings, really crucial stuff.
Because they're strong but light. Right,
yeah,
that's the big advantage.
Precisely. Incredible strength for their weight. But there's a catch. When you take these flat, strong sheets and bend them into shapes like L shapes, T-joints, C-curves, things you absolutely need structurally.
Yeah, I can see how bending might cause issues, like trying to fold thick cardboard really sharply. It always wants to crease or tear at the corner.
That's a perfect way to put it. In these composite parts, that corner, that curve, is where you get the specific failure mode called delamination.
Delamination. Okay, so the layers are coming apart.
Exactly. It's essentially a crack that runs through the thickness of the material. The layers literally keel away from each other, especially right there in the curve where the stress concentrates. It's kind of the weak link.
So engineers are trying to fix this weak link. What are the key metrics they're focused on?
Well, there are two main things. First, managing the high interlaminar radial stress. That's the ILRS. It's the force pulling those layers apart.
Okay, reduce the pulling apart force.
Right. And second, achieve better curved beam strength, or CBS. That's basically how much load the whole curved section can take before it, fails catastrophically.
Makes sense.
Yeah.
Higher strength, less stress between layers.
Yeah.
So what's the potential fix we're looking at today?
The study we're diving into explored using non-woven veils. Think of them as really thin, fibrous sheets.
Like a fabric layer?
Sort of, yeah, but non-woven. And the idea is to interleave them, place them between the main composite layers during manufacturing. And the big questions were, does the veil material matter? They tested carbon versus glass. And does the amount of veil material, its density, change things?
So not just adding reinforcement, but figuring out the right kind and the right amount. Does more always mean better? Let's find out.
Right. So why is this extra reinforcement even needed? If you look at typical FRP laminates, all the strength comes from the fibers laid out in the plane, lengthways or crossways.
But not through the thickness.
Exactly. There's usually nothing specifically designed to hold the layers together vertically. So when that ILRS starts pulling upwards in a curve, there's not much stopping the layers from just splitting.
Okay, so it's a known issue. People must have tried fixing this before these veils, right?
Oh, absolutely. Engineers have been creative. For instance, there's something called the tufting technique.
Tufting? Like on a cushion?
Sort of. It involves actually stitching threads right through the composite thickness. And that did help. Studies showed it could boost ILRS by around 40%.
Okay, interesting. What else?
Another approach used tiny metal pins, specifically stainless steel Z-pins, that basically drive these pins through the layers.
Like tiny nails holding the layers together.
Pretty much. And that was quite effective, too, boosting the curved beam strength, the CBS, by up to maybe 42%.
Both sound kind of invasive, though, sticking threads or metal pins through the structure.
They are, yeah. They work, but they do introduce potential new issues, like stress around the pins or threads. The veil approach seems, gentler. It works with the layering.
Right. So tell us about the specific setup in this study. What materials did they use for the main composite?
They used a fairly standard setup, unidirectional glass fibers and an epoxy resin, made using hand layup, then compression molding to cure it. Pretty typical stuff.
And how did they test the strength of these L-shaped samples? You mentioned making sure the failure starts in the right place.
Yes, that was critical. To really isolate the effect of the veil on stopping delamination, you need the crack to start consistently. You don't want it starting randomly somewhere else.
So they needed to pre-damage it slightly.
In a very controlled way, yes. They embedded a very thin copper wire, just 0.2 millimeters thick, right at the middle layer interface.
Okay.
Smack bang in the center of the curved part between the 8th and 9th layers. This little wire acts as a crack initiator.
A guaranteed starting point for failure.
Exactly. So when they did the bending test, a standard 4-point bend test, ASTM D64.10, they knew the crack would start there. Then they could measure how well the different veils resisted that crack's growth.
Clever. So it's a true test of delamination resistance, not just overall bending strength. Okay, let's get to the results. That sounds promising. Okay, before we see how the veils performed, what was the starting point? The strength of the sample with no veil.
Good question. The baseline sample, just the glass epoxy composite they labeled it GEC, its curved beam strength, CBS, was around 710 Newton millimeters per millimeter.
710 N a millimeter. Okay, that's our benchmark.
That's the number to beat.
Now, they tested carbon veils first, and they tried different amounts, different densities, 15, 20, and 30 grams per square meter.
Sure.
Which one came out on top?
Well, the results here were really striking. The absolute winner was the lowest density carbon veil, the 15 G-emitter one, codenamed GEC-15C.
The lightest one performed best. How much better?
Significantly better. We're talking an increase in CBS of about 88% over the baseline. It went from 710 up to roughly 1335 NSML.
Wow, 88%. That's almost double the strength just by adding this incredibly thin, light layer of carbon veil.
It's a huge improvement, yeah. And it wasn't just the overall strength. The interlaminar radial stress, ILRS, the force trying to split the layers, also saw a big improvement, about 57% better.
Okay, so how did this tiny amount of carbon achieve such a massive boost? What did it look like microscopically?
When they looked at the fracture surface with a scanning electron microscope and SIM, the mechanism became clearer. With the 15 G-emitter carbon veil, the crack couldn't just slice cleanly through.
It had to work harder.
Much harder. The researchers described the crack path as tortuous. It had to kind of meander and snake around the carbon fibers in the veil. This created what they called a cohesive failure zone. It took a lot more energy to break. The veil really integrated well.
A tough, winding path for the crack. That makes sense. But here's where it gets weird, right? Because you'd think, okay, 15 G-emitter an hour is great, let's add more. What happened with the 20 and especially the 30 G-emitter carbon veils?
This is the real surprise, the paradox. Adding more carbon didn't just give diminishing returns, it actually made things worse. Significantly worse.
Worse than the 15 G-emitter one.
Way worse. The sample with the highest density carbon veil, GEC-30C, had a CBS that was 43% lower than the champion 15 G-emitter sample.
Along 43% weaker? By adding more reinforcement, that seems completely backwards.
It does, doesn't it? You actively weaken the structure by putting more carbon in.
Why? What's the explanation? Carbon is supposed to be super strong and stiff.
That stiffness is actually part of the problem here, especially at higher densities. Carbon fibers have a very high modulus. They don't stretch much. When you pack too many of these stiff fibers closely together in that thin veil layer,
it becomes like a rigid barrier.
Exactly. It hinders the epoxy resin from properly flowing and creating a good bond with the main composite layers on either side. You lose that essential deformability you need at the interface for stress transfer.
So the dense carbon veil basically prevents the layers from sticking together properly. It creates weak spots.
Precisely. Instead of reinforcing the bond, it disrupts it. This leads to stress concentrating in small areas, and the whole thing fails much earlier. Brittle failure.
And the stats back this up.
Clearly, the improvements in ILRS for the 15 and 20 G-emitter carbon samples were statistically highly significant, really tiny p-values, less than 0.001. But the 30 G-emitter sample, it showed a statistically significant reduction in ILRS. The numbers confirm it was actively detrimental.
Wow. So less is definitely more when it comes to high-stiffness carbon veils.
Okay, what about the glass veils then? They're less stiff. Do they show the same pattern?
No, and that's what makes this comparison so interesting. Glass fibers are much less stiff than carbon lower modulus. They tested two densities, 25 and 30 G-emitter.
And what happened is they increased the density for glass.
The trend completely flipped. With the glass veils, the load carrying capacity and the curved beam strength actually improved slightly as the density went up from 25 to 30 G-emitter.
So more glass helped a bit.
It did. The 30 G-emitter glass veil sample achieved the best result for glass, getting about a 17% improvement in CBS over the baseline sample with no veil.
Okay, 17%. It's an improvement, but nowhere near the 88% boost we saw with the low-density carbon.
Not even close. But the key point is the trend. For glass, adding more material didn't cause that catastrophic drop-off in performance. It actually helped, albeit modestly.
So why the difference? Why can glass handle higher density? It comes down to flexibility, or deformability, as the engineers call it. Because glass fibers are less stiff, even when packed more densely in the veil, they remain more compliant.
They can bend and move more easily with the resin.
Exactly. They don't form that rigid barrier like the dense carbon did. This allows the epoxy matrix to flow around them better, create a better bond, and the veil itself can deform more to absorb energy as a crack tries to form. It distributes the stress better.
So the lesson seems to be about matching the material properties. If you use something really stiff like carbon, keep the density super low, or you mess up the bonding.
That's a great way to summarize it.
But if you use something more flexible, like glass, you have more freedom to add more material without causing those bonding problems.
Precisely the engineering principle here. But there's another important detail regarding the glass veils.
Oh.
While the CBS showed that modest 17% improvement when they looked specifically at the interlaminar radial stress, the ILRS, well, the improvements for both the 25 and 30 G-meter-augmeter glass samples were statistically not significant.
Not significant, meaning the improvement could have just been random chance.
Pretty much. The p-values were relatively high, 0.14 and 0.07. So, while the overall strength went up a bit, the glass veils weren't reliably tackling that core delamination stress nearly as effectively as the low-density carbon veil did.
Okay, so the carbon veil at 15 geometers was the clear winner, both in overall strength and in significantly reducing that critical interlaminar stress. The glass helped a bit overall, but wasn't as targeted.
That's the picture the data paints.
It's one thing to see the numbers, but you mentioned the SEM images earlier, the microscope pictures. Did they visually confirm these different behaviors?
They absolutely did. The visual evidence from the SEM was really compelling and lined up perfectly with the mechanical test data.
So what did the fracture surface look like on the baseline sample, the one with no veil?
It looked, well, weak. The glass fibers from the main composite layers seemed loosely attached to the epoxy matrix around them. You could almost see where they just pulled right out. It screamed weak interface.
Just peeled apart easily, like you said.
Yeah, classic adhesive failure between layers. Now contrast that with the champion, the 15 G-meter carbon veil sample.
What did that one look like after breaking?
Totally different story. You saw clear signs of matrix deformation. The epoxy itself had stretched and flowed before it fractured, meaning it absorbed energy.
Not just a clean break.
Not at all. You also saw features called river lines on the matrix surface, which again indicate the crack had to fight its way through, dissipating energy. And critically, the fibers, both the glass from the main layers and the carbon from the veil, looked really well embedded within the matrix. It looked like one solid, cohesive unit failed together.
A tough break, literally. It confirms that tortuous crack path idea.
Exactly. Now what about the ones that performed poorly? The higher density carbon veils, 20 and especially 30 genometers.
What did their failure surfaces show?
They showed signs of trouble. You could see things like fiber traces, basically marks left where fibers had pulled out cleanly, suggesting poor bonding again, lots of matrix cracking. And maybe most tellingly, evidence of crushing.
Crushing, like the material itself got pulverized.
Yeah, localized crushing of both the fibers and the matrix. This points directly to those stress concentrations we talked about. The load wasn't distributed, it focused intensely in small areas because of that stiff, poorly bonded veil, leading to a sudden, brittle, almost explosive failure.
Wow. The pictures really tell the story, don't they? Weak bonding for the baseline, strong, cohesive failure for the best performer, and brittle crushing for the high-density carbon.
It's a perfect visual confirmation of the mechanics at play. Hashtag tag, 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 outro.
Okay, let's wrap this up. This deep dive really highlights that when you're engineering with advanced materials, it's not just about throwing strong stuff at a problem, it's about finesse.
Absolutely. Precision is key.
So for you listening, maybe you're designing something with composites or just interested in materials.
Yeah.
What's the absolute core takeaway here?
I think the main message is that enhancing strength in these curved parts requires a careful balance, especially when interleaving materials. You need to consider the stiffness of the reinforcement, its modulus, and how much of it you're putting in its areal density.
And we found that the sweet spot was actually using a low amount, 15 geometers, of a high stiffness material, carbon.
Yeah.
That gave the best result, nearly doubling the strength.
Right, because that specific combination provided enough reinforcement to make the crack path difficult, but it was sparse enough to still allow flexibility and good bonding between the main layers. It forced that energy-absorbing, cohesive failure.
So what, for anyone actually building things, is interleaving works, but you have to tune it. Stiff stuff needs to be used sparingly at the interface. More flexible stuff gives you more leeway on density, but the performance boost might be less dramatic.
That's the practical design guideline coming out of this. It's about managing that interface, flexibility, and bond integrity.
Now, this whole discussion was focused on preventing delamination in a curved part under bending load, right? A specific type of failure.
Yes, primarily static load causing interlaminar tension.
So here's something to chew on. How might these insights, this balancing act between stiffness and density, ensuring flexibility and bonding, apply to other ways composites can fail?
That's a great closing thought. For example, what about impact damage tolerance? When something hits a composite structure, you get complex stress waves, potential delamination, fiber breakage. Could carefully designed interleaving, maybe even using different veil types in different areas, help contain that damage better? How does this stiffness versus density trade-off play out under dynamic high-speed loading?
Applying these lessons to things like bird strikes on aircraft wings or intact protection in vehicles. Fascinating stuff to consider.
Definitely a rich area for future research, building on principles like these.
Well, thank you for guiding us through the intricate mechanics of making curves stronger. Really insightful stuff.
My pleasure. Always fascinating to see how materials really work.
And thank you, our listeners, for joining us on the deep dive. We'll catch you on the next one.